Welcome back, physics fans. This is Varun Yarabarla here with the final lab, Lab 5, Choose Your Own Adventure Lab. We could choose anything to observe for this lab while using prior knowledge of V, idle, and tracker. We've done a lab on everything we've learned in this course so far except collision, so I chose to go more in depth with this topic. My adventure was observing the motion of a maximally inelastic collision between a moving car and a stationary car. The point of this lab was to analyze a real video and its data to quantify a collision, and then to compare the findings with the model in Python to determine if momentum is actually conserved and to see how the energy changes. The main result was that the observational data fit the model and momentum was conserved. There was also a loss in kinetic energy during the collision. The data did not fit perfectly with the model because of frictional force, which had not been accounted for in the computational model. The relevant systems and models in this lab are the momentum principle and the energy principle. The momentum principle states that the change in momentum is equal to the net force times the change in time. But during a collision, the net force is zero, so the change in momentum is zero, and momentum is conserved, as can be seen in the model. And with the energy principle for maximum inelastic collisions, the final kinetic energy is not equal to the initial. So the change in the internal energy changes whether it is a loss of heat, vibration, or deformation. So that is the equation for the change in internal energy, which I put into the model. I chose this video, which I found on YouTube, because it merely shows two cars that are magnetic on the ends that collide and exemplify a maximally inelastic collision in order to analyze and get real data for my lab. I tracked the motions of car 1 alone and of car 2 alone. When they come together, I also track the combined center of mass for both after they stick and move. This is what it looks like after I tracked it. I chose the origin to be where car 1's center of mass starts. The calibration length is set to be 0.25 meters, which is the length of the cars. On the right here has the data and the graph for just car 1, car 2, and both together. I took all this data on the right and made CSV files for both cars individually so that it can be read into the code, which I'll show later. Both of these files have the x and y components for each car. I made a single position versus time graph of the center of masses for all three motions recorded. I took the numbers and calculated the velocities using change in position over change in time. Car 1 moved approximately 1 meter per second initially, and after hitting the other car, it moved approximately 0.5 meters per second. Car 2 was initially at rest, but after the collision, it moved approximately 5 meters per second as well. And the combined motion of the two cars once they attached for the maximally inelastic collision was 0.5 meters per second. So now I'm going to start with the computational model that I created to represent this adventure. These two portions of code are where the data from tracker is read in from the observed motions of red car 1 and blue car 2 in the video in order to compare it to the model movement which will be created. I initialized everything I needed here. I created 4 objects, 2 for the computational model and 2 for the experimental model. These fixtures are the tracks on which the cars will be moving. I initialized the mass of the cars here and set up the initial velocity of each as a vector. Here we have the other initializations. The v is velocity and p is for momentum. The kinetic energy of both cars are shown here using 1/2 mv squared. The total kinetic energy is just the sum of both of these. The while loop shown here is used to update the position of the cars. When the code is run and the model shows up, the observed motion appears on the top, and the model created by the computational model is shown below. In fact, they should be run on top of each other, but I moved the computational model down by -1 meters in the y direction in order for it to be easier to compare the movements and differences of the two models. At first, only one object is moving and the other is at rest. After they collide, they get stuck together and move with a different velocity, just like maximally inelastic collisions do. So I printed the final velocity of the two combined, which is about half the initial at 0.53 meters per second. The next thing is the change in momentum, which there's no change. The last thing printed is the change in internal energy, which is 0.081 joules. So there was a loss of energy, and I used the equation of final kinetic energy of the two minus the kinetic energy of the initial to solve for that. Here, the model moves further than the observed because the model doesn't account for friction. The values the model gives do differ from those I got when calculating the observed values. If you look at how each of these calculations were done, you can understand why. For the observed motion, the initial momentum of the total system was 0.30 kilogram meters per second. The final is 0.29 kilogram meters per second, which shows that the momentum was mostly conserved with only a 0.01 kilogram meters per second of a difference, even though the velocities are different. So the momentum was conserved within 3% error, which fits with the data of the model that had a value of 0 for the change in momentum. The calculation of kinetic energy shows that there was a loss of approximately 0.089 joules based on the observational data, but the model shows a loss of 0.081 joules. The reason for both of these differences is because the model did not account for the frictional force, and the main error was mainly due to inaccurate placement of the center of masses in tracker. Going back to the main result, you can now see how the kinetic energy changed and the overall energy changed. The kinetic energy was lost and momentum was conserved during the collision. The combined masses were moving at 0.5 meters per second the whole time, which is approximately half the original velocity of car 1. Now let's answer the questions. Question 1. The main way to tell that this is a maximally elastic collision is because the two objects do stick together once they collide. This is for sure because the cars are magnetically attracted to each other on the ends. The change in kinetic energy is also not equal to 0. Question 2. Yes, the reason for getting 0.01 kilograms meters per second is because of not precisely pinpointing the center of masses on tracker. In reality, momentum is conserved when the two cars collide. The momentum is properly calculated with only 3% error. Reducing the error would require almost perfect and steady hands in tracking the motion. Question 3. If the model was run again, the observed motion and the computational motion models would both move the same distance in the same exact way.